numerical, you can have one more question, and that is show that motion of bar magnet you can say bar magnet or magnetic needle in a uniform magnetic field is SHM. Also calculate time period and frequency. Also calculate time period and frequency. So you have to show that motion of magnetic dipole in a uniform magnetic field is SHM, and you also have to calculate the time period and frequency. So see, if this is magnetic field, and in this magnetic field, I place a dipole having a magnetic moment M. So it could be a bar magnet or a magnetic needle. I place this at an angle theta. This magnetic field will exert a torque over this bar magnet. Torque on magnetic moment. Magnetic moment is, this is the torque on magnetic moment, which is mb sine theta. Now this magnetic moment could be of bar magnet or this magnetic moment could be of needle. So whatever the system is, the torque is mb sine theta. I'm putting a negative sign just to show that this torque is restoring. Restoring means this torque is trying to align the dipole along the way. The restoring torque, this torque is trying to align the dipole in the direction of magnetic field. It's a restoring torque. So this is the restoring torque minus of mb sine theta. Now, if I say that oscillations are small, this angle is small. For small oscillations, you can simply write your sine theta as equal to theta. So I can write this as it's minus of mb theta. I'm not giving detail of SHM. In chapter number 1, we have discussed SHM in much detail. And this is the same question that I did in chapter number 1. Just instead of magnetic moment, there was electric dipole. That's why I'm not giving you detail of SHM. It's minus of mb theta, which can be written as tau is equal to minus of k theta, where k is mb. K is equal to mb. This is known as spring factor. Angular frequency of bar magnet omega can be written as the ratio of k by I. Your k is mb, so it's mb by I, where I is the moment of inertia. Moment of inertia of bar magnet. If you want, you can write your omega as it's the ratio of 2 pi by t. So it's root over mb over I. So from here, you can write your time period as it's 2 pi root over I by m. Okay, the next thing is magnetic pole strength of bar magnet. So this is a bar magnet. This pole strength is M. Pole strength is M. Length of the dipole is M. Pole strength means strength of this north pole and strength of this south pole. See, the magnetic poles basically are not at the corners of the bar magnet. They are somewhat inside. This is somewhat inside. So if I take the geometric length of the bar magnet, then this is the geometric length. This is the geometric length from this point to this point. This is the geometric length. But the pole which you say north pole or you say south pole are not exactly at the corner. They're somewhere inside. So this is north pole and this is south pole, then this is the magnetic length. This L is geometric length and this L is the magnetic length. This L is L magnetic length, and this is the geometric length. So it's very clear that geometric length is greater than magnetic length. Magnetic length means the separation between the north pole and the south pole. Geometric length means the length of the dipole or the length of the bar magnet. So you can say that geometric length is greater than the magnetic. Is it clear? The concept of magnetic length and geometric length? There's one more thing in it. Magnetic pole strength, we have discussed even yesterday that magnetic pole strength is like strength, it's like charge in electrostatics. The strength of this north pole and south pole is represented by magnetic pole strength. Now, if I cut this magnet, let's say this is a magnet. If I cut this magnet, this is the north pole and this is the south pole. Pole strength M, pole strength M. If I cut this magnet in this way, then pole strength will not change. If you cut a magnet perpendicular to its length, if its area, this area of cross section is not changing, that magnetic pole strength will not change. So even when you cut this magnet into two parts, this is north pole having pole strength M. This is south pole having pole strength M. In fact, this will become a south pole having a pole strength M, a north pole having a pole strength M. So on dividing a magnet perpendicular to its length does not affect the pole strength. So cutting a magnet perpendicular to its length does not affect pole strength. Pole strength will remain same. But if I break this magnet, the same magnet, in two parts parallel to its length, like if I divide this magnet into two parts which are parallel to its, like I divide this magnet in this way, into two parts. So now pole strength will get half. Earlier it was in, now it will be in two magnets having pole strength of m by 2 and pole strength of m by 2. So pole strength of m by 2 and pole strength of m by 2. So if I cut a magnet in this way, so on cutting a magnet, you will use all these concepts in numericals. On cutting a magnet parallel to its length in two equal parts, pole length would be halved. Pole length would be halved. Solve one question on this concept. You have a bar magnet. A bar magnet having pole strength M and length L. That is the first part of the question. Calculate magnetic moment of bar magnet. Just calculate the value of magnetic moment for this bar magnet. In the second part, just divide this bar magnet into two parts. This is North Pole, this is South Pole. Into two equal parts. This is L by 2 and this is L by 2. So bar magnet given in part 1 is divided into two parts. Calculate magnetic moment of each part. In part 3, I'm dividing the same bar magnet into two parts in this way. This is bar magnet. I'm dividing it into two parts parallel to its length. So the two bar magnets will look like this. The length of each part is L. Bar magnet given in part 1 is divided into two equal parts. As shown. Calculate magnetic moment of each part. So the formula of magnetic moment is pole strength, which is M multiplied by L. So I'm writing the answer of part 1. The part 1 is straightforward. M will be M into L. In the same way, calculate magnetic moment of second and third part. So this is magnetic moment M. This is magnetic moment M. If I calculate magnetic moment then of each part, that will be pole strength M multiplied by length of each part, which is ml by 2. If I solve this thing, then get divided into two equal parts. This is m by 2. This is m by 2. This is m by 2 and this is m by 2. So the magnetic moment here is, it's m by 2 multiplied by L. So this is how we calculate magnetic moment if you divide a bar magnet into parts. Is it clear? Okay. So that's enough for a bar magnet. There is one more small topic in this chapter, and that is earth magnetism. After earth magnetism, chapter number 5 is finished. Then we'll do chapter number 6. It's a very small topic. See, basically, earth magnetism is a topic of geometry. It's a topic of geography, not physics. In your syllabus, just introduction of earth magnetism is there. See, what is earth magnetism basically? Let's see introduction of this thing. See, if you take a freely suspended magnet, then that freely suspended magnet always align itself in north-south direction. Means north pole of the magnet always align towards the north pole of Earth, geographic north, and the south pole of the magnet align towards the south pole of Earth, geographic south. So it seems like there's something on the north pole of the Earth which is attracting the north pole of the magnet, and there's something on the south pole of the Earth which is basically attracting the south pole of the magnet. So this attraction basically shows that Earth itself behaves like a magnet. Earth itself behaves like a magnet. Earth has some magnetic field of its own. Due to that magnetic field, a freely suspended bar magnet experiences an attractive force. The north pole of the freely suspended bar magnet experiences an attractive force towards the north pole of the Earth, and the south pole of the freely suspended bar magnet will experience attractive force towards the south pole of the Earth. Due to these attractive forces, these magnets get aligned itself along north-south direction. So, we will study magnetic field of Earth. Magnetic field. Yes, Fatma, I'm coming to it. Basically, the geographic north of Earth behaves like the south pole of the magnet. I'm coming to it. So, a freely suspended magnet align itself along north-south direction, which shows that Earth itself behaves like a magnet. There are plenty of other evidence for the magnetic field of Earth. Like if I take a piece of iron, let's say I take a scissor and I start rubbing that scissor with a magnet. What will happen after some time? That scissor will get magnetized, right? If I take a scissor or if I take a needle and starts rubbing this needle with the magnet, then due to by placing this needle in contact with the magnet, this needle acquires some magnetic properties. Needle get magnetized. Have you observed this thing? So if you rub a magnet or a needle or a scissor, a piece of iron with a magnet, then that magnet gets that needle or that scissor get magnetized. In the same way, instead of rubbing this iron piece with a magnet, if you place that iron piece, bury that iron piece into the earth, then after a certain time, that iron piece may get magnetized. Basically, the magnetic field of earth magnetizes this piece of iron. All these evidence show that earth itself behaves like a magnet. Earth has some magnetic field of its own. So in this chapter, we will study the magnetic field of Earth very briefly. Now, origin of Earth's magnetic field. Origin of Earth's magnetic field. So here we will see what's the cause for the origin of Earth's magnetic field. There are plenty of theories for the origin of Earth's magnetic field. Out of those theories, two theories are very famous. The one is the Earth magnetic field could be due to the charged particles trapped around the surface of Earth. So the first theory says, let's say this is Earth. This is an axis which is passing through the center of Earth. Oh, Jumana, I'm discussing it. Why it have what? I'm just discussing. So if this is Earth, this Earth is rotating about its axis. Around the surface of Earth, you have some charged particles. Basically, with cosmic rays, some charged particles came. So around the surface of Earth, there are some charged particles. Say if those charged particles at rest and Earth is rotating, then with respect to Earth, if from the Earth you look at the charged particle, you feel like at Earth is at rest and charged particles are revolving around it because motion is relative. So this is Earth, which is rotating. There are charged particles around the surface of Earth, around the atmosphere. Due to rotation of Earth, it seems like that charged particles are revolving around the Earth. And due to this motion of charged particles with respect to Earth, a current came into the system because current is due to the motion of charged particle. And that current can generate some magnetic field. So this could be the one reason for magnetic field. That magnetic field could be due to the motion of charged particles around the Earth. So you can write it as this cosmic rays may be source of magnetic. The exact cause is not known. Two prominent theories are there. The one theory is this, that around the surface of Earth, we have some charged particles, which is basically due to ionization of gases due to cosmic rays. And when Earth rotates, these particles are in motion with respect to Earth. The motion of these charged particles may generate current, and that current may generate magnetic field. Then there is one more theory. The second theory says, so the core of Earth is solid or it's molten. The core of Earth is solid or it's molten state. Okay, Fatma, you are wrong, Fatma. Johanna, yes, Johanna, you are correct. Johanna, the core of Earth is molten, right? Fatma, core of Earth is not solid; it's molten. Molten. If you go deep inside the Earth, then you will have lava. Lava, which is basically iron, nickel in liquid form. Core of Earth is molten and hot. At the core, temperature is so high that even the iron present within the core gets liquefied. So the core have iron, nickel in the liquid state. It have ions of nickel and iron. So the core of Earth have ions of nickel and iron. Just tell me, if Earth rotates, then these ions will rotate. Does that constitute current if ions are rotating? At the core of Earth have ions of nickel and copper. So if Earth rotates, all these ions are rotating. They are in continuous motion within the core of Earth. So what do you think? Does these moving nickel and iron ions constitute current? Yes, Jubena. If say what is current? Current is flow of charge. So if electrons are moving, it's current. If iron ions are moving, that means charged particles are moving, that will constitute current. So these rotating nickel and iron ions may cause current, and that current can generate magnetic field. So the circulating ions in core of earth form current loops and hence produce magnetic field. And hence produce magnetic. Okay, just note it down. So these are the reasons for Earth's magnetic. Next, see some definitions related with Earth magnetic field. It's a very dry topic. It's basically geography, not physics. So this is Earth. This is one axis which is passing through the center of the Earth. This is the North Pole, geographic North Pole, and this is the geographic South Pole. And this is the axis of Earth, which is known as geographic axis. So geographic axis basically an axis which is passing through geographic north and geographic south. This is the center of the Earth. Now, if you take a freely suspended magnet, that freely suspended magnet would always align itself along this direction. If I take a freely suspended magnet, then that magnet will align itself in this direction. This is the south pole of the magnet, and this is the north pole of the magnet. So usually north pole is attracted with the south pole, but the north pole of the freely suspended magnet, this is your freely suspended magnet. Now, since freely suspended magnet attract towards the geographic north, then you can conclude that the magnetic pole here that we call magnetic north, but it's not north pole, it's basically south pole. Near the geographic north, the pole is magnetic north of the earth, but the behavior of this magnetic north is like a normal south pole. And here, the magnetic pole that you have here is known as south pole, magnetic south. So the pole where the north pole of the magnet is aligned is known as magnetic north, and the pole where the south pole of the bar magnet heads is known as magnetic south pole. But basically the north pole, the property of this north pole is like south pole. We call this pole as north pole just due to the fact that this is near to geographic north. We should not have any confusion in giving direction. Just to avoid any confusion, we are writing this north. This as magnetic north, this is geographic north. But actually its properties are same as that of a magnetic south pole. So if I draw magnetic field lines, then magnetic field lines are like this. They enter from this region and leave at this region. Usually magnetic field lines don't enter at North Pole, they leave at North Pole. But here they are entering at North Pole. That means this North Pole behaves like a South Pole of a normal magnet. In the same way here, magnetic field lines are entering. They're leaving from South Pole and entering at North Pole. This again shows that these field lines are This north pole is basically a south pole and the south pole is basically a north pole. These are magnetic field lines here. So it's magnetic north and this is magnetic south. Is it clear? So someone was asking that why magnetic north pole of a bar magnet aligned towards the north. Towards north, the pole is known as magnetic north, but its property is like south pole of a magnet. Then we can take one axis an axis which is passing through the magnetic north and magnetic south of the earth. And this axis is known as magnetic axis. This axis is known as magnetic axis. This is known as magnetic axis. Axis which is passing through, this is magnetic south. Means south pole of earth magnetic field. This is magnetic north. Magnetic north means north pole of earth magnetic field. So this is the entire system. So these are some definitions that we will use. Geographic axis means an axis passing through geographic north pole and geographic south pole. The north pole of earth magnetic field is basically a south pole. Geographic magnetic axis is an axis which is passing through magnetic north and magnetic south. So we can write few definitions here. The first definition is of magnetic axis. So magnetic axis is basically axis passing through north and south pole, of Earth's magnetic field. It is inclined to geographic south at some angle which is around 20 degrees. It is inclined at 20 degree with geographic axis. That's magnetic axis. After magnetic axis, we have few planes, like one is magnetic meridian. See, magnetic meridian is basically a plane which is passing through this freely suspended magnet. If you take a freely suspended magnet, a magnet which aligns itself in north-south direction, then you take a plane. If I take a plane in this way, which is passing through this freely suspended magnet, then this plane is known as magnetic meridian. So it's a plane passing through freely suspended magnet. So the plane which is passing through a freely suspended magnet is known as magnetic meridian. And a plane which passed through this geographic north and geographic south. And if I take a plane, a two-dimensional plane, and I pass this plane through geographic north and geographic south, then that plane is known as geographic meridian. Geographic meridian. Plane passing through geographic north and south. So these are two planes. One is magnetic meridian and another is geographic meridian. Now, after these definitions, there are just three elements on which you can get few numericals. The next is elements of Earth magnetic field. Elements of Earth magnetic field. So we have three elements of Earth magnetic field. See, what does element of Earth magnetic field means? In geography, if you want to know the exact location of any point on the surface of Earth, you require two angles. One is known as latitude, another is known as longitude. So you want to know the exact location of any point on the surface of Earth, then you just need the latitude and longitude of that point, right? In the same way, if you want to know the magnetic field of Earth at any point on the surface of Earth, you want to know the magnitude of magnetic field and the direction of magnetic field on any point on the surface of Earth, then you will require three terms, and those three terms are known as elements of Earth magnetic field. So elements of Earth magnetic field simply means parameters require so these are three parameters or three elements. If you know these three elements, you know the exact value of Earth magnetic field. The first element is magnetic declination. Magnetic declination is actually the error between the exact geographic north and the geographic north shown by your compass needle. So magnetic declination is the error in the true geographic north and the geographic north shown by your compass needle. Compass needle never gives the exact direction of geographic north. It gives an error depending upon where you are using the magnetic compass. In India, this error is less than 0.1 degree, but it varies from point to point. And that error is known as magnetic declination. The standard definition says it's the angle between magnetic meridian and geographic meridian. The angle between the magnetic meridian and geographic meridian. No, Johanna. A magnet never aligns itself in the direction of. Yes, it can align in the direction of magnetic axis or it can align in other directions too. It will align along magnetic axis if it is passing through the center of the Earth. But since your magnet is on the surface of Earth, say this is your geographic north, then your compass needle can point in this direction, it can point in this direction, or it can point in this direction, or it can point in this direction. That depends on at what point on the surface of Earth you are using your compass needle. Now, these things basically seem strange. Why it's happening? It's due to the surface geometry of sphere. Sphere is not flat; it's in this way. Due to the spherical geometry, on different point on the surface of Earth, your magnetic needle will point differently, and that's why the angle keeps on changing. We usually represent it by alpha, the angle between magnetic meridian and geographic meridian. Geographic meridian is always fixed, but this magnetic meridian, direction of magnetic meridian keeps on changing because magnetic meridian is the plane passing through your bar magnet. Where in whatever direction your bar magnet is aligned, your plane would be in that direction. So it's keep on changing. This direction of magnetic meridian keeps on changing. That's why the angle between magnetic meridian and geographic meridian keeps on changing with respect to the points on the surface of Earth or location on the surface of Earth. Or in a very small plain language, you can say it is the error between true geographic north true geographic north, and geographic north shown by compass needle. So this is magnetic declination basically. The angle between the true geographic north and the geographic north shown by the compass needle. That's magnetic declination. Let's do one basic question on magnetic declination. Just one question on magnetic declination. Yeah. The question says that declination at a place is 15 degree west of north. In which direction should a ship be steered so that it reach a place due east? See, the question says this is your geographic north and south. These are your geographic axes. This is your geographic north. This is geographic south. This is geographic east. And this is geographic west. Geographic east means actual east. This is actual east and this is actual west. Now, your bar magnet or your compass needle is showing north 15 degree west of north. So this is basically the direction of your compass needle. This is the north which is represented by your compass needle. This is giving an error of 15 degree. So compass needle shows north at an angle of 15 degree west of north. This is the north of the compass needle and this is your actual north. So it's asking in which direction should a ship be steered so that it reach a place due north. So with respect to compass needle, this must be east. So this is the north of your compass needle. This is the east of your compass needle. Okay, now can you tell me at what angle you should steer this ship so that it reach this east? You will steer your ship at this angle, na? From here to here. At this angle you will rotate your ship. So that's not 90 minus 715, that's 90 plus 15. You want to take ship from this position to this position, so you will rotate the ship at 105 degrees. So these are the type of questions that you can get on magnetic declination. After declination, the next element is magnetic inclination or angle of drift. Basically, these terms declination and inclination are in context with a device known as dip circle. One angle is below the horizontal, another angle is above the horizontal. That's why one declination, another inclination. But I'm not coming to dip circle it. Magnetic inclination or angle of dip. See what is inclination and what is angle of dip. Okay, uh, just guess in which plane your magnet should rotate. It will rotate in geographic meridian or it will rotate in magnetic meridian. Your magnet should rotate in a plane where the magnetic field exists, right? Your magnet will rotate in a plane where your magnetic field exists. So in which plane magnetic field of Earth exists? The Earth magnetic field doesn't exist in geographic plane. It exists in magnetic meridian, in the plane of Earth magnetic field. The magnet is rotating due to magnetic field of Earth. So it should rotate in magnetic meridian, not in geographic meridian. So this magnetic inclination comes from that due to rotation of magnet in magnetic meridian. I'm writing it again. Total strength of Earth's magnetic field exists in magnetic meridian. So if I can draw both magnetic meridian as well as geographic meridian. This is my magnetic meridian and this is my geographic meridian. This is magnetic meridian where the total strength of Earth magnetic field exists, and this is geographic meridian. The angle between magnetic meridian and geographic meridian is declination. And say the total strength of Earth magnetic field exists in magnetic meridian. So let's call this as B. This is the total strength of Earth magnetic field. This is total strength of Earth's magnetic. So and this is a horizontal line in magnetic meridian. In magnetic meridian. And this is a vertical line in magnetic meridian. So this angle between total strength of Earth magnetic field and a horizontal line in magnetic meridian is represented by delta, and this is angle of it. So the angle between total strength of Earth's magnetic field and horizontal line in magnetic meridian. This angle is known as angle of dip. Is angle of dip. So after this, there is one last element of Earth magnetic field, and that last element is known as horizontal component. So as the name suggests, this is just the component of total strength of Earth magnetic field along horizontal. That's horizontal component. So horizontal component is just component of Earth's magnetic field along horizontal. Along horizontal. Okay, can you tell me how much, what's the component of B along this direction? I call that component as H. I will call this as V. What's the component of B along this direction? It's simple vector resolution. Yes, it's B cos delta, not alpha. See, this is B. This is horizontal. Angle between horizontal and B is delta. So it's not alpha, it's B cos delta. Okay, now tell me the vertical component. What is the vertical component along this direction? See, vertical component is this B sine delta. It's simple resolution of vector. You have this vector B here, this angle delta here. I'm asking you the horizontal and the vertical component. Horizontal component is B cos delta, vertical component is B sine delta. It's B cos delta and B sine delta. So V is B sine delta, that's equation number 2. Next, what you can do is just divide 2 and 1. So this is horizontal and this is vertical component. Always remember horizontal as equator. So the equator of Earth is like this horizontal component. Vertical means poles. So I better write this as, this is like poles, or pole of Earth. And this horizontal line is like equator. This slight angle between equator, because this is the equator. Not this one, but this variation is very small, some 2-3 degrees. So I will consider that horizontal line as equator and this vertical line as pole. So this is the component of Earth magnetic field. It's B cos delta and B sine delta. Now we can take the ratio of these two components. If I divide 1 into, then you can write V by H is B sine delta by B cos delta, gets cancelled out. V by H comes out to be tan delta. Now, if I add V and H, squaring, adding 1 and 2, squaring and adding 1 and 2. Okay, can you guess if I square 1 and 2, what will I get? I will get that H square, not 1, not exactly 1. I will get H square plus B square is B square sine square delta. Yes, you are right. This, if I take this B square as common, then this is H square plus V square is B square. This is sine square delta plus cos square delta. Yes, that is one. Then I am left with H square plus B square is B square. So I can write that your B is root over V square plus H square. So if you have vertical and horizontal component, then you can calculate the total strength of Earth magnetic field. Remember, B is total strength of Earth magnetic field. Okay, do one more thing. Calculate the values of horizontal and vertical component at poles. At poles, delta is 90 degree. Calculate how much is H and how much is V. And then calculate these values at equator. At equator, your delta is 0 degree. At equator, delta is 0 degree. So H is B cos 90, which is 0. Your vertical component is V sine 90, which is B. Horizontal component is B cos 0, which is B. Vertical component is B sine 0, which is 0. So these are the horizontal and vertical components at pole and at equator. Okay, so let's erase it. So that was about Earth's magnetic field. That was last topic, Earth's magnetic field. Let's do few numericals on this concept. Delta is 60 degree. H is 0.4 into 10 raised to the power minus 4 Tesla. So using this, you can calculate, first you can calculate V. See, V by H is 10 delta, right? So you can write that yours V by H is tan 60. So yours V by H is root 3. Your V comes out to be H root 3. So your H is 0.4 into 10 raised to the power minus 4 root 3 Tesla. So this is the value of vertical component. So once you have vertical component, horizontal component, you can calculate B. You can even use, you can calculate B using this relation, B is root over, or there is an easier method. Your V is B sine delta, right? So your V is, it's 0.4 into 10 raised power minus 4 root 3 is B sine 60. It's root 3 by 2. So it's 0.4 into 10 raised to the power minus 4 into root 3 is B. Sine 60 is root 3 by 2. So this root 3 will cancel this root 3. B is 0.8 into 10 raised to the power minus 8. So this is the total strength of Earth magnetic field, which is 0.8 into 10 raised to the power minus 4. There is one last topic in Earth magnetic field, that is, no, not in Earth magnetic field, basically in natural magnetism. The natural magnetism earlier had three parts. The one is Bohr Magneton that we did. The second is Earth magnetism. There is one more portion which is classification of Earth's magnetic material in ferromagnetic, paramagnetic, and diamagnetic. But that portion is removed as a deleted portion. But even from that portion, there is one topic which is magnetic moment of a revolving electron. You can get that question in terms of numericals of magnetic moment. So just to be safe side, I am taking that particular topic, magnetic moment of a revolving electron. Although this is the deleted one, but you can get questions based on this topic, because it can be directly related to magnetic moment of a current carrying coil. Magnetic moment of a revolving electron. You can also say this is Bohr magnet. It's a very simple calculation. Say you have an atom. It's considered a very simple atom, hydrogen atom. This is the nucleus of the hydrogen atom. Around this nucleus, electrons are revolving. Basically, there is one electron, single. This electron is revolving. The radius of the orbit is r. Now, since electron is moving, due to the motion of electron, the system will have current. The direction of current is opposite to the direction of motion of electron. So if it is moving clockwise, then your current is anti-clockwise. So if T is time period of electron, time period of revolution of electron, if it is the time period of revolution of electron, and E is electronic charge, then current associated with motion of electron. Okay, now tell me, if you have charge and time period, how much is current? Fast. Current is charge upon time. It's I by T. That's current, its first equation. So due to motion of this electron, the system will have current, which is charge upon time. Now I need to calculate this time period in terms of velocity. We can write velocity as distance by time. Just tell me how much distance this electron will cover if it complete one revolution. Yes, 2 pi r. And the time is t. So from here you can write that your time period is, it's 2 pi r by v. I can substitute 2 in 1. When I substitute 2 in 1, the current comes out to be E by T. So it's E by 2 pi r into V. So that's the expression of current. I is EV by 2 pi r. This is correct. Okay, now tell me the expression of magnetic moment. What is the expression of magnetic moment of a current carrying coil? We represent the magnetic moment associated with the electron as mu. Associated with revolution of electron, or that you can say orbital motion of electron around nucleus. So that is mu L, that's NIA. For one turn, you can write this as IA. That is equation number 4. The area of the coil is pi r square. If the radius is r, then you can see this revolving electron behaves like a current carrying coil. The area of the coil is the radius of the pi r square. That's 5th. So I can substitute the value of I from this equation 3 and the value of A from equation 5. So I can substitute 3 and 5 in 4. When I substitute 3 and 5 in 4, I will get that magnetic moment is EV by 2 pi r into pi r square. Pi gets cancelled out this pi, r will cancel out with the square. And the orbital magnetic moment mu L is EVR by 2. Next, we will calculate the angular momentum of electron. So in 11th, you must have done angular momentum. If a body is moving in a circle of radius r, then its angular momentum could be written as mvr by 2. So from here, this is angular momentum. You can write that your VR is, it's 2L by m, that is equation number 7. So if I substitute this equation, it's not MVR by 2, it's MVR, sorry, it's just MVR. So no 2 here. So VR is L by m now. So this is the orbital moment. The magnetic moment of a revolving electron is E by 2m into L. From here, you can take this ratio mu L by L, which is E by 2m. E is 1.6 into 10 raised to the power minus 19 electronic charge. M is electronic mass, which is 9.1 into 10 raised power minus 31. If you solve it, you will get this is 8.8 into 10 raised to the power 10 coulomb per kg. So this ratio of mu L by L is known as gyromagnetic ratio. This is equation number 8, and this is known as gyromagnetic ratio. It's like charge by mass ratio. It's a gyromagnetic ratio. Okay, after this we can do one more thing. The one more thing we can do is, in equation number 8, your mu L is EL by 2M. Okay, have you heard about Bohr's atomic model? Have you heard about Bohr's atomic model? So there were certain postulates in Bohr's atomic model, right? So one of the postulate in Bohr's atomic model is, in Bohr's model of atom, angular momentum of electron is quantized. Means your L is nh by 2 pi. This equation I take from Bohr's atomic model. Bohr's atomic model simply says that angular momentum of electron is quantized, means it have fixed values where n is 1, 2, 3, h is Planck constant, and this is what you call the number of orbit. The number of orbit or shell, your K element shell. You must have done this in class 11 chemistry. First chapter, atomic structure. So L is nh by 2 pi. So if I substitute 9 in 8, if I substitute L here, then I will get that mu L is, it's E by 2m into L. L is nh by 2 pi. So your mu L is ENH by 4 pi m. So mu L is n into EH by 4 pi m. Where n is the number of orbit, it could be 1, 2, 3 and all. So if you look at this thing very carefully, E is constant, H is constant, 4 is constant, pi is constant, m is constant. Only this n is variable. So the magnetic moment will have values which are multiple of n only, integral multiple of. For minimum magnetic moment, so this basically shows that magnetic moment is quantized. This shows that magnetic moment is quantized. See, quantized means the value, the quantity cannot have arbitrary values. Its values are fixed. If you look at this expression, h is Planck constant fixed, 2 is fixed, pi is fixed. L can have only those values which are multiple of h by 2 pi. It can have 1 into h by 2 pi, 2 into h by 2 pi, 3 into h by 2 pi, nothing else. Or 4, 5, 6 h by 2 pi. Just like in this way, the magnetic moment is n into h by 4 pi m. Your n could be 1, so it would be eh by 4 pi m. 2 into h by 4 pi m, 3 into h by 4 pi m. The values are fixed. It's multiple of eh by 4 pi m. That's why we say that magnetic moment is quantized in this expression. The magnetic moment is quantized in this expression. So can you tell me the minimum value of this magnetic moment? 1. Yes, n is 1 and your magnetic moment is EH by 4 pi m. And this is what we call Bohr Magneton. This minimum magnetic moment associated with a revolving electron is what we call Bohr Magneton. So this minimum magnetic moment of revolving electron is Bohr Magneton. So this minimum magnetic moment is known as Bohr Magneton. So this is Bohr Magneton. We take mu B is EH by 4 pi m. Say all are constant. If I substitute all these values, then the value of Bohr Magneton comes out to be 9.27 into 10 raised to the power minus 24 ampere meter square. So this is the value of Bohr Magneton.